Let's talk about radioactivity or nuclear physics or how we're all going to die anyway. Now, what do I mean by nuclear physics? It has everything to do with the nucleus of the atom. So the word nuclear comes from the term nucleus. So most of the discussion has to do with what's in the nucleus of an atom. Now, this unit in general is split into a couple or maybe three broad categories in my mind. We'll talk about the structure of an atom and the details of what an atom is, what's a mass number, what's a proton number, what's an isotope, yada yada. Then we'll discuss the radioactivity portion of the unit. So what is radioactive decay and what kind of radioactive emissions are emitted from an unstable isotope and so on. And then we'll finally talk about the properties of decay, so half-life and the applications of radioactive isotopes and so on. But before I start, friendly reminder, this list that you see is what the syllabus wants you to know. This is exactly what the syllabus needs you to know for every single topic that you have. So I highly recommend you use this like a checklist. So for example, if you read this, describe the structure of an atom in terms of a positively charged nucleus and a negatively charged electron that orbits around the nucleus, if you understand what that phrase is, you're fine. You're on the right track. If you don't, make sure to revise the point that this topic's discussion or that line is discussing. Okay. But anyway, let's get started with the structure of an atom. You know, the boring stuff. You all know what an atom is. It's the building block of matter. The word atom means indivisible. So nothing smaller than an atom, but we know that's not true. An atom consists of what we call a nucleus. And inside the nucleus, you have two different particles called protons and neutrons. And outside the nucleus, orbiting in different energy levels and energy shells, you have electrons, right? Now, protons, neutrons, and electrons have both mass and charge. It's very important that you remember they have both mass and charge. Now, they do have values in kilograms and in coulombs, but we're not going to study them in terms of kilograms and coulombs. We're going to study them relative to each other. So I say a proton has a mass of 1U, a neutron has a mass of 1U, where U is short for the unified atomic mass constant or unit mass constant or atomic mass unit. It has so many different names. But in the end, U has a specific value, which is 1.66 10 to the power of negative 27 kilograms. Do not memorize this though. Just understand that protons and neutrons have the same mass. Electrons have a mass of about 1 over 2000 U. So compared to protons and neutrons, electrons have negligible mass. Protons have a positive 1 charge, electrons have a negative 1 charge, and neutrons have no charge, 0 charge. But again, neutrons have 0 charge because they actually have both positive and negative charges in equal amounts. A neutron is technically a proton plus an electron stuck together, which is why it has the same mass as a proton, but it has no charge because positive 1 and negative 1 cancel out. Right? This will be relevant later when we talk about beta decay or the decay of beta particles. Okay? Good. Now, then when we write down elements, we use what we call a nuclide notation. This is called a nuclide notation, where you write the name of the element using its proper symbol. So helium, for example, 4 and 2. This 4 is the nucleon number or the mass number, which is the number of protons plus neutrons. And this 2 is the proton number, which is the number of protons. Elements are all defined by their proton number. Elements are all defined by the proton number. Okay? So you can have multiple isotopes, and we'll discuss them now, but as long as they have the same proton number, they're the same element. If I want to find the number of neutrons, it's always the mass number minus the proton number. Easy peasy. So what's an isotope? An isotope is an atom of that same element, which means it has the same number of protons, but a different number of neutrons, which means the mass number or the nucleon number is different. So here's an example right in front of you. You have carbon 12 and 6 and carbon 14 and 6. They both have 6 as their proton number, but this has 6 neutrons and this has 8 neutrons. They're all called isotopes though. Now, before we move on, we want to talk about the alpha scattering experiment, which was an experiment performed by Ernest Rutherford, a very long time ago, to prove the structure of an atom. I won't get into the story or the background behind the story or the lore behind it, but just to simplify things, the way this experiment worked was, number one, we got a very thin gold foil. So get a very, very, very thin piece of gold. So thin, in fact, that this little bit of gold is almost one atom thick, as in it's so thin, it's almost one atom thick. And then we got a source of alpha particles. So an alpha particle is a positively charged particle that's emitted by radioactive isotopes. It also has a mass and proton number of 4 and 2, so just like helium. The important thing is this alpha particle is positively charged and is heavy. And then we fired, or Ernest Rutherford fired all of these alpha particles, all right, at, like by putting it in a box that only emits them in one direction, at the gold foil. The purpose was to find out the structure of an atom, like what's inside an atom. So we ended up with 3 observations here. Okay, let's move this back in the center. Okay, roughly. We ended up with 3 observations. Most of the alpha particles that went through or hit the foil went through without deflecting. This means that these alpha particles hit nothing. Some alpha particles, and let me choose a different color here for a second. Some alpha particles deflect, meaning they change direction. It's not a lot, but if some do, and they deflect at different angles. Whereas a very tiny, very small number of alpha particles reflected backwards. So this experiment had 3 observations. A lot of alpha particles just went through that very thin piece of gold. Some alpha particles deflected, meaning they changed direction. A very small number of alpha particles deflected backwards. Or reflected, but I like deflected backwards. Now, since we have observations, we should have conclusions. Conclusion number 1, since most of the alpha particles, this is us zooming inside the foil, since most of the alpha particles did not change direction, this means that most of the atom is just empty space. There's nothing inside. It's empty. Whee. Now, because some alpha particles deflected, meaning they changed direction, this means that they were repelled somehow. Because the only way for a positively charged particle to change direction is to experience another, repulsion. Now, sure, you could say attraction, but you'll see why I insist on saying it's repulsion for now. Since alpha particles are positively charged, these alpha particles are positively charged, then they have to also move something close to something that's positive, which means the nucleus that's inside is positively charged. That's observation number 2. Conclusion, sorry, number 2. Conclusion number 3, because a very, very, very small number get deflected back, like reflected back, these are the alpha particles that manage to hit the nucleus directly. This shows me 2 things. Number 1, it proves that the nucleus is extremely small in size, so very small. And it also proves that the mass of the nucleus is very large, it's very heavy. Because if the alpha was heavier than the nucleus, the alpha would have shot the nucleus away. But it didn't. The alpha got reflected back, which means the nucleus is very heavy. So we say the nucleus has most of the mass of the atom. So to summarize again, there are 3 observations and 3 conclusions that you have to memorize. Observations are most alpha particles were not deflected, some were deflected, and a very small number deflected back. Conclusions, there's a very small nucleus, and mostly there's empty space. That nucleus is positively charged, and the nucleus has most of the mass of the atom. You must memorize each observation with its conclusion. Like you need to link each observation with its relative conclusion, right? That's what you primarily need to memorize. As for the details of the experiment, all you need to remember is we fired alpha particles at the thin gold foil. Here are the results. And second, you need to be able to sketch this. So if I show you an alpha particle that's about to hit a nucleus, gets repelled. Far away from the nucleus, just goes through. Close to a nucleus, changes direction. Okay? Very good. Finally, we have a couple of nuclear reactions called nuclear fission and nuclear fusion. If you recall, nuclear fission is the splitting of a large nucleus into smaller nuclei. This is what we use the nuclear power stations to generate heat, which boiled water and, produced steam, and the steam generated electricity through the turbine and generator. You get the idea. You don't have to memorize the formula, but I need you to know how to balance these equations and to understand that uranium is usually the one being split. And we split it by, letting it absorb a neutron. But then when it splits, it has to split into two smaller atoms and maybe a few neutrons. So what's the mass and proton number of a neutron? Let's start with that. A neutron has a proton number of 0, it has no protons, and a mass number of 1, because it's one neutron. Anything else you don't memorize. You just have to complete the equation. So I could give you this value missing, and I could also give you the question with this value missing, and you should be able to complete this equation by balancing the mass numbers and the proton numbers, which means the mass number before this reaction, so 236, should also be equal to 236. So how do we do that? It's the, barium plus 92 plus 3, because that's 3 neutrons. So what's the value of the barium? You get the idea. Okay? Same thing with the proton number. The proton number needs to be balanced before and after the decay. So 92 plus 0, which is 92, should be equal to 56 plus whatever this is going to be plus 0. So 92 minus 56 gives you this missing value. Anyhoot. Moving on. The opposite of nuclear fission, which means to break, is nuclear fusion, which means to what? To join. Nuclear fusion, which is to join. So two of these are added together. So it's usually hydrogen, by the way. We add two hydrogen atoms, we fuse them, and they form into helium. This, I would argue, try to memorize. At least memorize the elements involved. Like, you know that hydrogen gives you helium. That's what you need to remember. That's all. Because we use this here, and we use this in space physics when we discuss the sun. You get the idea. But it follows the same thing. Look at this. 3 plus 2 is 5. Then what about this side? 4 plus 1 is also 5. 1 plus 1 is 2, and this side is 2 plus 0 is 2. The mass and proton numbers are always equal on each side. So no, it's never less than 1. Why are you claiming that it's less than 1? 235 plus 1 is 236. 141 plus 92 plus 3, because it's 3 neutrons, so 3 times 1, is also 236. It'll give you the same mass number. Mass number is never less. Proton number is never less. These have to be conserved. All right, let's solve a question or two. The scattering of alpha particles by a thin metal foil supports the nuclear model of an atom. Why are alpha particles used? Let's read. Because they travel slowly. I don't think so. Because they are heavy. Heavier than what? The neutrons? Is that why we use them? Because they're heavier? Heavier is not the issue. No. The reason we use alpha particles is because they're what? They're positive. So when they hit the nucleus, they get repelled. Or when they get close to the nucleus, they get repelled. So no, they have positive charge. That's why we use them, because they're positive. Okay, next, an iron nuclide is represented by this symbol. This is iron, by the way, so 56 and 26. Which statements about a nucleus of this iron... Okay, let's read that again. Which statement about a nucleus of this iron? We're not talking about electrons here. We are not discussing electrons in orbit here. So this nucleus contains 56 neutrons. No, it would be 56 nucleons. So no. The nucleon number is 30. No, the nucleon number is 56. That's the mass number. The number of neutrons is 30. So no. The proton number is 26. Yes, that's it. It's a 26. That's correct. So it's only 3. D. Next. A nuclear power station has a reactor where controlled nuclear fission of uranium takes place. What is meant by nuclear fission? All right. It's when a large nucleus is split into smaller nuclei. Wait a second. No way that's worth 3 marks. Well, yeah, it isn't. Because during that reaction, something else also gets emitted. Emitting or producing energy. It always releases energy. All right? Keep that in mind. So back here, splitting of a large nucleus into a smaller nuclei, that's great. Perfect. For maybe a mark or 2. But if I want more, please add energy to the mix. All of these reactions release energy. Okay, state one advantage and one disadvantage of generating electrical power in nuclear power stations when compared to electrical power generated only using wind. Now, this is a Unit 1 question. So the advantage of generating electrical power using nuclear power stations is that it's what? Reliable. Meaning it produces electricity and is unaffected by the weather. I would add that. All right? And then, what's the disadvantage of nuclear power stations? Is that they produce nuclear waste. Or you could say they're non-renewable. Or you could say they are non-renewable. All right? Very nice. Excellent. So let's continue about. Deuterium is an isotope of hydrogen with 1 proton and 1 neutron. Nuclear fusion occurs. Now, you need to read carefully. Sure, I said you don't have to memorize. Again, you don't have to memorize the different, the different elements and such, but look at the description. Learn from the description, all right? So learn from the description you have on hand. Okay. Deuterium, which has 1 proton and 1 neutron. When 2 of deuteriums combine and an isotope of helium and a neutron are formed. Use the nuclide notation to write down this equation. So let me write down the elements first. You have H plus H equals He plus N. That's exactly what the question even stated, not what I've memorized. But what are the mass and proton number here? For hydrogen, it's 2 and 1. How do you know that? Because they have 1 proton and 1 neutron, so 2 and 1. What about helium? Well, I'm not sure. I know helium is 2, but hold on for a second. You should memorize the neutrons, 1 and 0. Can you balance this equation? I was like, yeah, that's 2 plus 2. So the other side must also equal 4. So this can't be 4. This has to be 3, because this is 3 plus 1. So it's actually an isotope of helium, which is true. That's what he said exactly. It's an isotope of helium. There you go. Now, we have a question. Isn't that worth 2 marks? Oh, you mean the first one? No. What are the 3 marks for? Large nucleus. You've identified that the nucleus in question is large. It's heavy, right? Splits. That's the second mark. That's the action. That's what nuclear fission is. Releasing energy. Producing energy. That's the third mark. Okay? You don't understand why you aren't supposed to add the 2 and 2? I did. What's 2 plus 2? Quick math. What's 2 plus 2? 4. all of this must be 4, not just the helium. All of this must have a mass number of 4. So it's 3 plus 1 that gives you 4. More quick math. Aha. See? Good. Now, next question. Figure 9.1 represents all the particles in a neutral atom. I'm sorry, one last question. Isn't hydrogen 1 and 1? Yeah, but he told me this is an isotope of hydrogen with 1 proton and 1 neutron. I'm not using what I've memorized. I'm using what the question has given me. What's the mass number of something with 1 proton and 1 neutron? 2. Okay? That's why it's 2 and 1. In this question, it's 2 and 1. Figure 9.1 represents all the particles in a neutral atom of radioactive isotope X1. Determine the number of neutrons in this atom. Explain how you obtained the answer. So this is more of a logical thing. If you have a neutral atom, this means that the number of electrons in orbit is equal to the number of protons inside. How many electrons do we have? I have 1, 2, 3, 4, 5. Since it's neutral, what here has 5? The white dots or the gray dots? You can count 1, 2, 3, 4, 5 white dots, which means the white dots are the protons. That means the gray dots are the neutrons, which means how many neutrons do you have? 1, 2, 3, 4, 5, 6, 7. So that's 7 neutrons. So how did I get that answer? I mean, it's only worth a mark. So how did I get that answer? Since the number of electrons equals protons, I can just skip. The gray dots or circles are the neutrons. Or you can say the white dots or the white circles are the protons. As long as you've identified what are you counting. Hey, I know that these are equal to the protons, which means the other things are the neutrons. The gray dots are the neutrons. Very nice. Let's move on to the arguably the most important part of this unit, radioactive decay. When you have, it's a big checklist, by the way. When you have an unstable atom, any kind of unstable atom, like the uranium, for example, it will always emit radiation in order to become stable. That's why we mentioned isotopes earlier. Again, if you have an unstable isotope, some isotopes are unstable. When you have an unstable isotope, by the way, do you guys know why some isotopes are unstable? Like, are you guys familiar as to why some isotopes? Like, go back to isotopes for a second. Let's go back to isotopes for a second. No, that's not the isotopes section. Oh, this is it. Like carbon 12 and carbon 14. What's the problem? You're like, no problem. The problem is when an isotope has too much mass, an excessive amount of mass, too many neutrons, it becomes unstable. Most of the time, when the number of protons is equal to the number of neutrons, which is why you'll always see the mass number double the proton number for most stable elements, it's stable. The forces inside kind of balance out. But when you have an excess of neutrons, then you have an unstable atom. It's not always the case, but most of the time, that's the reason why it's unstable. Sometimes because it has excess energy. But for now, the reason why some isotopes are unstable is because they have too many neutrons. Now, unstable isotopes emit a piece of themselves, right? They emit a piece of themselves, which we call radiation or radioactive emissions, in order to become a nice and what? Stable isotope. Now, I'm going to discuss this process in a bit in detail. However, we want to focus more on the radiation bit first. When I say radiation or radioactive emissions, what do I mean? Scientists discovered that there were only three types of radioactive emissions produced by any unstable isotopes, and they are called alpha particles, beta particles, and gamma rays. Alpha particles, beta particles, and gamma rays. What's an alpha particle? It's when a nucleus emits two protons and two neutrons. That's what it's made of. What's a beta particle? It's when it emits one electron. What's a gamma ray? It's just a wave. And we've studied that in waves, if you recall. Good. Now, each one of these particles or wave has properties like mass and charge and nuclide notation, but then it also has what we call ionization or ionizing power or range or penetration. All right? So we're going to discuss all of these properties now in one nice big chunk. We're staying here for a bit. Since an alpha particle is made up of two protons and two neutrons, it has a mass number of 4 and a proton number of 2, or a mass of 4 and a charge of 2. That's why it's 4 and 2. Beta particles are made of 1 electron, which means they have a mass of 1 over 2,000 and a charge of -1 because it's 1 electron. 1 over 2,000 U, if you recall. Gamma has nothing because it's a wave. Now, the way we write the notations as an element, the nuclide notation, for alpha it's 4 and 2, which is just like helium. This is why we sometimes call alpha particles helium nuclei, or an alpha particle is similar to a helium nucleus, not a helium atom, a helium nucleus, because nuclei don't have orbiting electrons. A beta particle is either written as beta 0 -1 or E 0 -1 because it's an electron, so 0 because it has no mass number, and -1 because it has a -1 charge. Gamma has nothing. All right. Now, when it comes to radiation itself, like radioactivity, when you have something that's radioactive and it emits radiation, the issue with the radiation that's being emitted, like if I tell you that, I don't know, like every other human being in the world or parent would like tell you your phone is radioactive and you will die if it's on your face, to keep you away from your phone. Is that true? Is your phone radioactive? No. Sure, it emits different types of waves, but it doesn't emit alpha particles or beta particles or gamma rays. The problem with with all three, alpha, beta, and gamma, is that they are all ionizing. So what does the term ionizing mean? To ionize means to make something into an ion. This means you either remove or add electrons. In the case of radiation, any type of radiation removes electrons from an atom that it hits. So by default, an atom is neutral because it has an equal number of protons and electrons. But when an alpha particle just smashes through, as I like to always joke around, it came in like a wrecking ball, and it shoots, it like completely destroys the electrons in the way. This atom is no longer an atom, it's now an ion. Now, for non-living things, if something is ionized, that's fine. It can conduct electricity now. Like in the case of air that's ionized, as in exposed to radiation, can conduct electricity. Because it has free moving, ions in the air, positive and negative charges. But for living organisms, we have a little bit of a problem. What's the problem? We are made of atoms. Our cells are made of atoms. Our DNA is made of atoms. So when something goes in and completely starts picking out electrons from your atoms and removes them, your cells end up either dying, that's the good ending, or your cells mutate if their DNA is affected, which turns into, cancerous cells or tumorous cells. And you end up dying. So either way you end up dying, sadly. Either way you end up dying. So ionization is harmful for living organisms because of either cellular damage or cellular death or cellular mutation. This kills you either way. Now, Not all types of radiation are equally ionizing. Alpha particles, for instance, are very strongly ionizing. Like if an alpha particle goes through your atom, it's going to wreck you. Why? It has the most mass, most kinetic energy, and most charge. Like it's the biggest, heaviest, chunkiest of them all. Beta particles are less ionizing. They're strongly ionizing, but less than alpha. Why? They have less mass and less energy and less charge. Gamma rays are very weakly ionizing. Why are they very weakly ionizing? I'm sure you've realized the criteria here. Has no mass and no charge and very little energy. All right? But everything is balanced in life, except League of Legends. Now, everything is, I'm sorry, everything is balanced in life, right? Why? Sure, alpha particles are very strongly ionizing, but it can't really go through paper or even travel in air very far. Like if you let an alpha particle travel through air, it stops after about 10 centimeters. So range in air, you can just write 10 centimeters, for example. It stops. It loses energy. It loses it very quickly. If you have a beta particle, however, this can travel up to about 10 meters in air. So it goes several meters in air before it stops. Gamma rays, even though they're extremely weakly ionizing, they travel much farther, like about 10 kilometers in air or so. I don't even have a value for that. Like, who knows? It's a wave. Who knows when it stops? If you want to stop an alpha particle, you can stop an alpha particle by using a sheet of what? Paper. Alpha is stopped by paper, absorbed by it. It can't go through. Beta can go through paper, yay, but it's stopped by anything that's a bit more dense. So starting with aluminium, which means if you have iron or steel or anything denser or heavier, yeah, that stops alpha and stops beta. Then what about gamma? Now, gamma is very penetrative. It's stopped by almost nothing. In order to stop gamma, you need a very thick sheet of lead, which absorbs most of the gamma. Some of it goes through. Some of it goes through. But you need a thick sheet of lead or a lot of concrete. So very thick concrete. Big concrete buildings full of like 1 meter thick walls or 2 meter thick walls. Yeah, that stops gamma. Sure, it lets a little bit through, but gamma is already very weak. So if you make it even weaker, it'll be useless. So if I were to ask you, I want to store a radioactive isotope. Let's say my phone is radioactive. I want to store it in a box to completely 150% stop any radiation coming out of it. Uh, where do I put it? In a lead box. Where do I put it? In a lead box. Okay, very nice. So that's the difference between alpha, beta, and gamma. Now, I'll mention this later again, but the process of decay, like the radiation emitted, is always random, as in you don't know which part of the atom is emitting that radiation, and it's spontaneous, meaning it's not affected by anything external. So if I were to heat my radioactive isotope, I wouldn't emit more alpha, or it would maybe change the alpha to beta. Like, no, none of these things in radioactivity are affected by anything external. It's a completely natural process that is completely unaffected by us as human beings. Okay, nice. Yeah. Do alpha and beta and gamma, do these things get affected by anything else? Like I can stop them by paper, stop them by aluminium or lead. Yeah, you can also change their direction because they're charged. At least alpha and beta are charged. You can change their direction. If you pass alpha, beta, and gamma through an electric field, meaning you put it between two metal plates, one is positive and one is negative. Because beta is negative, it turns towards the positive. Because alpha is positive, it deflects towards the negative. This makes sense, Opposites attract. Gamma is completely unaffected because it has no charge. But I want you to observe a second thing. Alpha and beta deflect in different directions, but the amount of deflection for beta is much greater than alpha's. Like alpha barely changes direction, but beta was like zoomed in, smashed into the plate as fast as it could. That's because beta has less mass than alpha, so it's easier to change its direction, even with the same force. Heck, it even experiences less force. Alpha has a positive 2 charge, beta has a negative 1 charge. Alpha actually experiences double the force. But because it's so heavy, it has a mass of 4u compared to the 1 over 2000 u for beta, alpha does not deflect much. It does not change direction very much because it's very heavy. Then, what about magnetic fields? Now remember, this is in magnetism. We're going to study, Fleming's left-hand rule, but let's use this right now. So here's my left hand. I know the recording might, like, my video might have been flipped. So let me check if I can flip that. This often keeps mirroring it, but yeah, I can't control the mirroring, sadly. But what I can do is make myself temporarily, I hope, bigger. So you can see me better. Oh, what big, teeth you have, Grandma. Anyway, using Fleming's left-hand rule, right? I'm doing this on the board in the opposite direction so you can see. Your index finger is the magnetic field. And it says that the magnetic field is into the page. And your middle finger is the current. So in this case, it's the alpha particle, because the current is the flow of positive charge. So the alpha particle. So your thumb shows you the force. So if your magnetic field is into the page and your middle finger is heading to the right in this direction, so right, as you can see over there, what's the force acting on the alpha particle? Upwards. So because of the magnetic field, alpha deflects up. Now remember, alpha is positive, beta is negative. So we'll always experience the opposite force. So it always goes down. With the same thing, alpha deflects less than beta because alpha is heavier. So we solve this using Fleming's left-hand rule. Right? How did we deduce that? Because what is a current? The flow of charge. And isn't a flowing alpha particle technically a current? If an alpha particle is positively charged, moves, isn't that a current? It constitutes a current? Which means having an alpha particle go through a magnetic field is like having a current go through a magnetic field. Use the Fleming's rules, as we are. But the current is the flow of positive charge, okay? Now, oh, I should make myself smaller again, shouldn't I? Before I start covering up the rest of the screen. Okay, next. Radioactive decay. What do I mean by radioactive decay? The process itself, the beginning of what we discussed. What is it? It is a process where the nucleus of an unstable isotope emits radiation to become more stable. Good. Now let's actually write down equations for the decay process, like see how the elements change. You've got your basic rules here, but I'm going to use examples to explain what's going on. First, let's say you have, we're going to use alpha decay as our first example. For alpha decay, let's say you have an isotope of uranium 235 and 92. And I tell you that uranium emits alpha. By the way, if an isotope emits alpha, it forever emits alpha. We discover what type of radiation is emitted by something, right? We don't control it, we discover it. So uranium emits alpha, 4 and 2. Plus, you end up with something else. Let's call it X. You need to find out what the mass and proton number are. Now, you're not memorizing anything except for the mass and proton number of alpha. You just need to complete this equation. How do we do that? Remember, total mass number before equals total mass number after. Total proton number before equals total proton number after. So 235 minus 4 gives you, let's change the color here, 231. And then 92 minus 2 gives you 90. Perfect, bravo. Everybody in chat answering the question correctly, that's exactly it. Which means you lose 4 in your mass number and you lose 2 in your proton number. Now, do you know what that means? This means that X is not uranium anymore. The proton number has changed, so it's not the same element. This is important. When decay occurs, the element changes. Okay. Next, what about beta decay? Carbon 14 and 6, which I mentioned earlier, is a known beta emitter. So if I tell you carbon 14 emits beta, so beta, which is 0 and -1, what are you left with? What is the X here? Remember, you just memorize the beta. However, you need to know how to complete the equation. 14 minus 0 gives you 14. Wait, nothing changed? Yeah. I'll explain why. I haven't explained why yet. 6 minus -1 gives you 7. Look at the math. It works out. 14 plus 0 is 14. 7 plus -1 gives you 6. That's fantastic. But do you know what that means? This means the mass number has no change. This does not change. But the proton number increases by 1. How? Yeah. This has to do with what is a beta particle. Remember, what is a beta particle? Go back up. Beta particle is 1 electron. Radiation is always emitted from the nucleus of an isotope. But technically, there are no electrons. Technically, there are no electrons in the nucleus, right? But no electrons in the nucleus. Actually, there kind of are. Remember how we talked about in the very first section when we talked about, what's a neutron? And I said a neutron is actually, technically speaking, a proton stuck with an electron. Anybody who studies advanced physics will know that, this is not perfectly true because there are things called quarks inside, so forgive me for that. But to simplify your life, assume for now that a neutron is actually a proton plus an electron stuck together. Okay? So when an isotope emits a beta particle, what happens is that one of the neutrons breaks into a proton and an electron. This becomes your beta particle and gets emitted out. So what do you have left behind? An extra proton. So essentially, during beta decay, you lose a neutron, but you gain a proton, which is why the mass number doesn't change. Because the mass number is the number of protons plus neutrons. So -1 plus 1 stays the same. However, it's no longer the same element. Since the proton number has changed, it's not the same, element. 14 and 7 is nitrogen, if you remember from your chemistry lessons. Okay? Again, what are you expected to do here then? What should I remember and what should I memorize? You should, number 1, know how to complete these equations by memorizing the values of the mass and proton number of alpha and beta, so that you can complete these equations. Number 2, you need to identify that, hey, it's no longer the same element. We don't use a periodic table. We don't memorize different elements except for helium because that's similar to alpha, okay? And then you need to be able to explain what happens to the atom or to the nucleus during decay. So for example, during alpha decay, oh yeah, you lose 2 protons and 2 neutrons. During beta decay, you lose 1 neutron, but you gain a proton. Excellent. Gamma has no mass and charge, so gamma has no equation. Next. I'll go back up for one more second. I want to go back to this bit over here. Oh, you don't see where I zoomed, where I highlighted? Let me zoom in. Let me zoom in some more. Let me zoom in some more. Let me zoom. I can't zoom in anymore. Physically, I can't, unfortunately. What's the problem here? I said that even lead doesn't 100% absorb gamma radiation, right? So right now, in the room I'm in, if I pull out a radiation detector, let's say my phone has a built-in radiation detector sensor or something, what's going to happen? If I switch it on in this room, will it measure zero? Or if you switch it on in your room, will it measure zero? No. Not because you're radioactive. Maybe you are toxic, but maybe not radioactive, right? So your radiation detector should not measure anything. But no, that's not true, because there is always radiation around us. We call that radiation that naturally exists in the environment around us background radiation. We call it background radiation. So even if there's no source, and you turn on a detector, it'll read a very small value, by the way. It'll read a value of about, I don't know, 10 counts per minute, or 20 counts per minute, or maybe even 30 counts per minute, or per second. The counts per minute, counts per second thing is the unit that most radiation detectors use because they count the number of ionizations that happen, right? We don't need to go into the details of how the detector works. Just know that it often measures what we call the count rate, which is the number of radioactive emissions per second. So there's always radiation around us. What's the source of these, measurements? Uh, the air is radioactive, so radon gas in the air. Rocks in buildings are radioactives because these are all natural things, by the way. Like the building I'm living in right now is made of walls, and the walls are made of bricks, and the bricks are made of, the clay and the sand and the rocks that we dig from underground. And all of these have small amounts of trace radioactive substances. So they emit radiation. It's normal, it's natural. Heck, the food and drink I eat and drink is like radioactive. Cosmic rays, meaning rays from outer space, like the sun, from other stars, that's radioactive. But all of this is nothing. It's tiny, right? But it does cause problems. It does cause problems whenever we try to measure radiation. Why? Let's say this is me. Look, I'm a stick man now. And I have a detector in hand. And as I look at the detector and I look at the reading, the detector reads, maybe I'm measuring the radiation from, a space rock or something. I don't know. But it reads 320 counts per minute. This is the detector reading. Is this the amount of radiation only by that weird space rock that I found? Like, is the space rock emitting 320 counts of radiation per minute? No, because detectors measure everything, including the background. So let's say, for example, I tell you, you have a background radiation count of 20 counts per minute. The detector reads 320 from the source. What is the radiation from the rock itself? From the source itself. What's the radiation from the source itself? 300. How do I know? Because 320 minus 20 is 300. This is the detector reading, which measures both the source and the background. So when we remove the background from the reading, you only get the proper value from the source. We call this correcting for background. So when I tell you, hey, this reading has been corrected for background, this means we've removed the background reading. But if I tell you this is a detector reading, this means it includes the background reading. So keep that in mind when we solve questions. Now we've already identified that radiation can kill us, either by killing ourselves or by mutating ourselves or by causing cancer, or by causing, radiation burns. Either way, we die. How do we try to avoid death from being exposed to radiation? Well, number one, don't get exposed. Number, obviously, nonetheless. Number two, let's say I'm actually using a radioactive source for a practical experiment. Like there's a legit reason for it, okay? It's a valid reason. One thing to do is to move far away from the source. That's logical and makes sense. The farther away from the source, the less it can affect you because it does get weaker over distance. Even beta does get slightly weaker over distance. So the farther away you are, the better. Reduce the exposure time, meaning if you have to use a radioactive isotope for any reason, some of it's medical, some of it's manufacturing related, just make sure you use it for a very short time and then go far away. Or if I'm going to inject you with a radioactive isotope, which is something we do to try and find cancer cells inside, a patient with cancer. Radioactive isotopes in the blood actually help us find where the cells exactly are. We don't put a substance inside you that lasts a long time. We want it to last a very short time and then run out. Or you could use a shield or a screen. You know how doctors, when they do x-rays, they always put you in a room. It's like, okay, are you ready? Okay. And they just run into a different room with a wall between you and them so they don't see you. Yeah, that's to keep them safe. And when storing it, remember, what's the best material? Lead. Make sure you use containers made out of lead. Now, you'll notice how I said that the boxes should be locked as well. The container should also be locked. This is because I remember a stupid question in the mark scheme in the exams a long time ago in the past papers, where I state a couple of precautions when storing radioactive sources. I was like, storing it? I use a container made of lead. What's another precaution? Like, what's a second precaution that has to do with storing? Turns out if you lock it, that's enough. That's the second precaution. Silly, but I know. Let's solve a few questions. During beta decay, one of the neutrons in the nucleus changes. What happens to the neutron? And what did I say? A neutron changes into a proton. The neutron changes into a proton. Obviously, it's a proton and an electron, technically speaking, but I only care about what's inside, right? It becomes a proton, right? If you want to be safe, and an electron. No, I won't say no. Or and a beta particle. Then, explain how the charge is conserved during this change. Like, how is the charge constant? Wait, is it kept constant? Well, hold on. What's the charge of a neutron? Zero, right? What's the charge of a proton? +1. What's the charge of an electron? +1. So the charge is conserved. So this is what I'll mention. I'll say, hey, neutrons have zero charge. Protons have a +1 charge. And electrons have a -1 charge. So +1 minus 1 gives you 0, which is true. Proton plus electron gives you 0. Gives you no charge. So it's conserved. There's no charge. Okay. Complete the nuclide equation for the alpha decay of radon-212 to form an isotope of polonium. The symbol for polonium is PO. Okay, so radon emits an alpha particle, so alpha plus Po. And then we need to fill in the values for alpha. So alpha is 4 and 2. And Po is, where's my calculator? 2 and 2, I don't need one. 2 and 2 minus 4 gives you 208. And 86 minus 2 gives you 84. I don't know that it decays into polonium. I only wrote PO because he told me it decays into polonium. Cool. Next. A radioactive source is placed near a detector connected to a counter. 210 counts are recorded in 3 minutes. The background count rate is 20 counts per minute. What is the corrected count rate for the radioactive source? Now look at this. All of them are in counts per minute. So this first value isn't given to me in the correct format. What do I mean 210 in 3 minutes? I want the number of counts per minute. So step one, I have to divide this by 3 so I get the number of counts per minute. So my starting value is 70 CPM, counts per minute. Now, if that's my starting value, that's the detector or the counter reading. What's the corrected reading? 70 minus 20. You remove the background, which gives you 50 CPM, which is the corrected background. Corrected, sorry, reading. So the answer is A. Nice. Now, let's finish up this unit by talking about our last section here. We want to talk about what half-life is and what are the applications for radioactive, decay or isotopes. First, what is half-life? Radioactive isotopes, when they decay, they become stable, right? That's the whole point. An unstable isotope decays and becomes a stable isotope. Yes? Yes. Then what? If you have a bunch of atoms that become more stable, doesn't that mean you're less unstable, which means you emit less radiation? So naturally, over time, the amount of radiation you give out does what? Decreases. Over time, the amount of radiation you give out decreases because you become more and more stable. Turns out, however, there's a certain calculation to it. Sure, we already said it's random and spontaneous, but there's a calculation to this. What's the calculation? There's something called half-life, which is defined as the time taken for half of the nuclei of an isotope to decay, or half of the radioactivity to decrease, right? What do I mean? Look at this. Let's say I have a substance over here with 20 million atoms inside, or 20 milligrams inside, or 20 whatever. If you wait for 20 minutes, you will only have 10 milligrams left that are unstable, meaning, and forgive me, I'm not going to do it randomly like I've done in this document, but half of it decays. This half is now stable, the other half is still unstable. If you wait another 20 minutes, think of the SpongeBob transition, a few moments later, or 20 minutes later. Well, the first half was already decayed. Half of the half decayed. So what do you have left? 5 milligrams. That's what's left. If you wait for another 20 minutes, another 20 minutes later, this has already decayed. This has already decayed. Then half of the half of the half will decay. So you're only left with 2.5 what? Milligrams, or 2.5 million atoms. The time it took to decrease by half is called the half-life, and it's constant. It's constant per element. Like iodine 131 is a radioactive isotope. That has a half-life of 8 days. It always takes 8 days to decrease by half. All right? Carbon 14, for example, I think has a half-life of 5,000. Yes, 5,700 years. So sometimes they have half-lives in the years. Some isotopes decay very quickly, in seconds. Technetium, for example, 99, is an isotope with a half-life of like what? 6 hours. So it depends. So how do we find half-life? Most half-life questions that come in the form of a graph are very simple. Step one, you look at the starting value. Like look at where the graph starts. In this example, it starts at 20, right? What is half-life? Time taken for it to decrease by half. So what's half of 20? 10. So you go look at 10, which is half of that starting value, and you go find the time it took to decrease to 10. That's 20. Okay? Which is 20 minutes in this case. What if you wait another 20 minutes? Look, the 10 decreases, it becomes 5. That's half of the 10. If we wait another 20 minutes, look at this. It's 2.5. And you get the idea. All right? Now, keep in mind though, that if a question includes background radiation, you have to remove the background radiation before solving for half-life. Like half-life questions here, like if I solve another example, just like throw in another example. If I say you have a substance that starts off with 50 milligrams of iodine 131, and I tell you the half-life is 8 days. How much iodine is left after 16 days? What do I do? Look at your total time, 16 days, divided by the half-life, which is 8 days. This means you have 2 lives. So if you start off at 50, you divide by 2 once, so that's 25. You divide by 2 twice, that's the second time. That's 12.5. That's your final answer. So the mass of the iodine that remains in the end is 12.5 milligrams. Solving half-life questions are easy. But especially with graph questions, if I give you a reading which includes background, you must remove the background count. We'll see that when we practice. I'll point it out. Finally, let's go over a few useful applications of radioactivity that you should roughly be familiar with. Like number 1, smoke alarms. These use a radioactive isotope. How do they work? You don't have to memorize the circuit very well, but you have to at least understand. The way it works is this. You have a source of alpha particles that ionizes some air between 2 metal plates. And you have a circuit. Now, here's the thing. As long as this air is ionized, this circuit is technically closed because the air conducts electricity. And it goes to a sensor that's connected to the alarm. As long as there's a current, the alarm is off. But as soon as there is any smoke that goes into that space, smoke is as thick or as good an absorber of alpha particles as paper, which means it stops the alpha particles from ionizing the air. The air is no longer ionized. It's now an insulator. So now there is no current. So the sensor detects that and goes, oh my God, there's no current. There is definitely smoke inside my detector. Sound the alarm. Or beep, 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 beep. It depends on where your smoke alarm is. Or, if you're in Egypt here, most houses don't have a smoke alarm, so we burn to death. Yay. Sorry. Now, sometimes I have a very crude sense of humor, don't you think? Yeah. Or dark. Regardless. So that's how a smoke alarm roughly works. What's another good application? We use it to irradiate food. Now, please note, there's a difference between being contaminated by a radioactive isotope and being irradiated by a radioactive isotope. To be irradiated means to be exposed to radiation. To be contaminated means I've licked that, uranium piece of uranium. Like it's on me now. The uranium is part of me now. So irradiating means I expose the food to radiation, which doesn't make it radioactive. We use gamma radiation to kill off any kind of bacteria in the food. So the food is now safe, especially in canned foods. They usually like heavily expose canned foods to radiation to make sure the cans are sterile and nothing bad is in there. Then, sterilizing equipment, medical equipment. What do I mean? If I have things like scalpels or forceps or things like doctors and surgeons use after cleaning them with, some nice soap and water and some Dettol maybe or something. And I dry them off. We put them inside a device that exposes them to gamma rays. This makes sure that every single tool has no viruses or bacteria on it whatsoever. We can also use it to measure or control the thickness of something while it's being manufactured. Like if I have a sheet of aluminum that I squeeze to make thinner aluminum foil, the way we measure the thickness is by using beta particles. If the foil is thin, I mean really thin, beta particles can still go through. But if the foil is too thick, the beta particles don't go through. So we use the reading on the detector to tell me if the sheet that's being manufactured is too thick or too thin. If the sheet is too thick, it'll absorb the beta and my reading decreases. That's bad. If the sheet is too thin, thinner than what I want, the reading increases because it lets more beta particles through. That's also bad. Depends on how I want to manufacture the sheet. Finally, we can use it to diagnose or treat cancer, as in to find out if somebody has cancer or not. We often inject patients with a radioactive isotope, which emits radiation. We put them inside a device, and that device measures that radiation and finds exactly where the cancer cells are. We then can use gamma rays to treat cancer by killing the cancer cells. We form the gamma rays into a laser beam, and we shoot the laser beam into the patient, or at least where the cancer cells are, to kill them off. Okay. Let's solve a few questions and then we'll be done. Almost done. The background count rate measured by a radiation counter is 40 counts per minute. So he's mentioned background. We're probably removing it from the next reading. With the counter close to the radioactive source, the counter reading is 960 CPM. The half-life of the source is 20 minutes. What is the counter reading 1 hour later? So let's go. What's my starting value? 960. Oh, but nope. I can't use this because this is the counter reading, the detector essentially reading. So second, I have to remove the background from it. This gives me what? 920. This is my source value. Now I need to use my half-life work. So he wants the reading after 1 hour, but the half-life is 20 minutes. 1 hour is 60 minutes, by the way. So how many half-lives will you have? 3 half-lives. In 60 minutes, you have 3 20-minute lives, essentially. So let's start my dividing. So 920 is my starting value. After 1 half-life, we get 460. After the second half-life, we get 230. After the third half-life, we get 115. That's it. So the answer is 115. Is it? Notice how he said, what is the counter reading after an hour? Not the source reading, the counter reading. Counters are stupid. They measure their source with the background. So the counter reading is 115 plus 40 again. So that's 155. Be very careful if a question wants the counter reading or the source value, essentially. For the counter reading, we'll always add the background back. Okay. Let's solve a slightly easier question. A sample of radioactive isotope has an initial rate of 128 CPM and has a half-life of 4 days. How long will it take for the rate of emission to fall to 32? Now, there's no background mention here, right? So I don't care about background. He said, my starting value is 128 and a half-life of 4 days. How long will it take to drop to 32? So, okay, pull out the calculator. After 4 days, it'll be half of 128, so divide by 2. That'll be 64. It's still not 32. So after another 4 days, it'll drop to 32. Oh yeah, I've gotten to it. So how many days in total did it take? 2. times 4 days, which is 8 days total. So let's see. Good. Next. This is the last question or last page. Figure 9.1 shows some properties and values for alpha and beta and gamma. Complete this table, complete the table. So let's go. Number of protons, 2. Number of neutrons, 2. Charge. What is this? We've never seen. Sir, you just said earlier we're not going to memorize values of charge. Yeah, you won't. But if I tell you that an alpha particle has a charge of positive 3.2 10 to the power of negative 19, this is the +2, remember? Beta has no protons and no neutrons, but what is the charge? Negative half of that. Negative, but half of that. Because if the charge of a beta particle is -1 and the charge of an alpha particle is +2, then it's half of whatever value I write. So what's half of 3.2? 3.2 divided by 2. This gives me 1.6. So the answer here is 1.6 10 to the power of -19 coulombs. By the way, that is the charge of an electron. It's called the elementary charge. It's usually called E, right? But you don't have to memorize this. I worked it out from the table. Gamma has no protons, no neutrons, and no charge, but it's stopped by what? Lead. A thick sheet, not thin, thick sheet of lead, L-E-A-D. All right, next. State how beta decay changes the nucleus of an atom. Remember, beta decay is when a neutron turns into a proton. Is when a neutron turns into a proton and emits an electron. But he's not asking about the decay process itself. He says, what happens to the nucleus? Well, yeah, so the nucleus loses one neutron, but gains one proton. Okay? Good. I'll show you the conservation of charge again later. Then last bit of this question, no, there are still safety precautions, but that's easy. A radiation detector used in a laboratory detects background count rate of 30. Okay, so that's my background. It's 30. Let's highlight that. A radioactive source is placed in front of a detector. The initial reading on the detector is 550 counts. Okay, so that's my starting value. The half-life is 25 minutes. The half-life is 25 minutes. Calculate the expected reading on the detector after 75 minutes. Okay. Well, first things first, I can't start with this. This is just like the multiple choice question result. What's my starting value? 550, but that's the detector value. So I remove 30 from it, which means my actual initial value is 520. Now I can start half-lifing it, like dividing it. But how many half-lives? In 75 minutes, I have how many 25-minute half-lives? 3. So we're going to divide this by 2, 3 times. So 520 divide by 2. By the way, if you want to, you can just divide it by 2 power 3, which is fine, by the way. But I like to do it this way so you can visually see it. So that's 1 half-life, so divide by 2, divide by 2, divide by another 2, which gives me 65. Remember, count the arrows, not the values that you see. You started at 520, the first change, second change, third change. So my reading is 65. Again, or is it? Does he want the source reading? Or does he want the detector reading? Detector. Which means what do I need to do? Take that 65 after it's been, after it's lost its, radioactivity, and add 30 back to it again. I need to add the background again to give me the detector reading, which is 95. Very good. It's the exact same method. Just be careful if you want the reading on the detector or the source. Finally, state 2 safety precautions taken when moving, using, or storing sources in a lab. So moving or using or storing, all of these have the same precautions. Maybe use forceps to hold the source, or like hold it far away from you, because I don't want to hold it myself, and store it in, or tongs, that's fine. Use whatever you want. Use tongs if you want. Go to the kitchen, pick up some tongs, but never put it back, please, because that is now contaminated. Store it in a lead-lined box, or store it in a lead box. Or using, since you also said using, was what? Reduce exposure time when using. That's also good. Can you touch the lead? Yes. Like the lead is safe. What's inside is not. That's the end of it? Yes, it is. And that, ladies and gentlemen, is the end of this unit. Pretty nice, pretty short.